Okay, today we are going to talk about the periodic table and the history of the periodic table. I'm going to try to get through both 5D and 5E in one video, so I may talk a little fast. Now, we've already learned about the periodic table. We've learned the basic structure. We've learned about where the metals and the nonmetals are. We've talked about noble gases, which are right over here. We've talked about the actinides and lanthanides. We've also talked about the fact that the numbers 1, 2, 3, and so forth are the number of protons. They determine the order. And we've also talked about the electron configuration and how that goes into it. But we're going to back up and talk a little bit about the history of the periodic table, where the structure came from, and how it's changed over time. By 1860, chemists had discovered more than about 60 elements, which obviously left several undiscovered, but they did not have set ways to determine atomic masses. And the International Congress of Chemists met to figure out this problem, and it was an Italian chemist, Cannizzaro, that actually proposed an accurate way to measure atomic mass, which was a pretty big deal at the time and allowed chemists and scientists to look at elements in a much different way. Now, at the time was a Russian chemist named Mendeleev, and Mendeleev, after he heard about the meeting, he decided to incorporate this atomic mass system into his new book. And for his new book, he essentially was trying to create a way to organize the elements according to their properties. Because he knew that there were patterns there, he just was trying to figure out the best way to identify them. And essentially what he did is he wrote all of the information on note cards about each element, and he kept organizing these note cards in different ways, looking for patterns and trends, and he eventually found them. And they said, history says that he landed with this method because he was a big solitaire player, and it was a way that he could keep rearranging the information in a quick way in order to see those patterns, to see how they materialized. And when he arranged them by atomic mass, which they finally could be able to do, he found that these properties showed up at specific intervals. Okay, or in essentially every certain number of atoms, you got an atom that had similar properties. It just had more electrons and more protons. And he identified this as what's called periodic. Actually, I'm not sure if he coined the term, but periodic means containing a repeating pattern. Okay, hence the periodic table. And he published his first periodic table in 1869. Now, he was not the only scientist or the only chemist to do this, but this was Mendeleev's periodic table. And you've got some things that are similar. You know, you've got hydrogen as a smaller element, lithium, and again, this is a representation of their atomic mass. So for lithium, we know it has 3 protons, but a neutral lithium is also going to have 3 neutrons, which gets us pretty close to 7. But the other thing I want to point out are these question marks here. He had a question mark above 45, he had a question mark above 68, question mark above 70, question mark above 100. There may be a few more, but essentially what those question marks were undiscovered elements. And this prediction right here is what set Mendeleev apart from all the other chemists that were trying to organize the periodic table. And he essentially left empty spaces where he predicted these undiscovered elements should fit. And this was a big kind of risk that he took in doing this, but when he was right and his predictions were confirmed, it really caused a lot of scientists and a lot of chemists to come on board. And the 3 big ones that were soon discovered were scandium, gallium, and germanium. They fit right where he said they would, and people were hooked. They were in. They knew this guy knew what he was talking about. Okay, so the next guy that comes along is Mosley. And what Henry Mosley is most responsible for is in 1911, he found that the pattern worked best if you arranged the elements by the number of protons, or the atomic number, which we've already talked about, and how we know the periodic table is now ordered, not by atomic mass. Now, you probably have not noticed this before, but if you look at a modern periodic table, there are some elements that are essentially out of order for atomic mass. So either take out a periodic table or flip back to the slide, because I'm going to point out what I mean. Okay, if we go to cobalt and we go to nickel right here, all right, I don't want to highlight that. If you look, cobalt has a atomic number 27, nickel is 28. But if you look closer at their atomic masses, cobalt is 58.93 and nickel is 58.70. Now, if we remember, these atomic masses are weighted averages of all of the masses of the isotopes that exist. So essentially they're out of order, as opposed to most of the time, like if you look at titanium and vanadium, the atomic number goes up from 22 to 23 and the mass goes up. But this is what Mosley switched. Some other pairs that are out of order: argon is 39.95, potassium is 39.10. And again, this is just because of the um, masses of the isotopes. The other one that's in the majority part of the periodic table involves tellurium and iodine at 52 and 53. As you go down the periodic table, there are a lot more exceptions, but these are kind of the three big pairs that you have: argon and krypton, cobalt and nickel, and then tellurium and iodine. So that was why Mosley's update was important. Now, periodic law is, remember, a law is an observation, is that physical and chemical properties are periodic functions of their atomic numbers. Or in other words, when you put elements in order by atomic number, elements with the same properties appear at regular intervals. Okay, and just as a reminder, physical properties are properties we can observe without changing a substance. Chemical properties, we do have to change it in order to observe it. Okay, now the modern periodic table is an arrangement of elements in order of atomic number. Again, that's our 1 to 118 number of protons, so that elements with similar properties fall in the same group or family, which is vertical. Okay, horizontal is going to be period. Chemists did make some very important updates or discoveries after Mendeleev's initial table. And here are some of one of the most important updates was the noble gases. If you look back at Mendeleev's original periodic table, none of the noble gases were listed. And that was just because they had not been identified yet. Argon was the first one that was discovered by Lord Rayleigh as well as Sir William Ramsay. It had been in the atmosphere, but since the noble gases are so unreactive, no one had detected it because they hadn't seen it in any chemical reaction, so they didn't even realize what they were missing. Helium was first discovered as a component of the sun. They used the electron spectrum of helium like we observed in class for hydrogen. And then in 1895, Ramsay again found it on Earth. Okay. Now, with the noble gases, Ramsay again discovered krypton and xenon in 1898. Once they found one, they knew what they were looking for. It went a lot faster. And then Friedrich Dorn discovered radon in 1900. And Ramsay proposed a new group for the noble gases. That's spelled wrong. But noble gases for the periodic table. So that was Ramsay's big update, is that he discovered a lot of the noble gases and he put them on the periodic table. Okay, now here comes my exciting joke for the day. It says two atoms are walking down the street. It says one atom to the other, "Hey, I think I lost an electron." The other one says, "Are you sure?" "Yes, I'm positive." If you don't get that, then we've got another set of problems, and we'll talk in class the next time that I see you. Okay, next section we got to do is electron configurations and the periodic table. Now we have already drawn on a periodic table and labeled it to look something like this. We had the S block over here where there's 2 electrons. We've got the D block where there's 10 electrons, 5 orbitals. P block, 6 electrons, 3 orbitals. F block, 14 electrons, 7 orbitals. And so a lot of times when we're talking about this, we need to refer back to this thought or the periodic table. So again, keep a periodic table handy and that will help you. Okay, so with the patterns, remember electron configuration is going to dictate chemical reactivity because elements in the same group will have similar chemical properties, and that's what we're really going for here. That's part of the reason we do these 2 sections together. Valence electrons. We haven't really talked too much, well, we talked a little bit about this, but these are the electrons available to be lost, gained, or shared in the formation of chemical compounds. That's what a valence electron is. They're found in the outermost shell, or the most outer energy level N. They're used to determine the atom's chemical properties. They also were the ones that were listed outside of the noble gas notation. So if we think back to, well, let's say sodium. Sodium's noble gas notation would be neon, and then it would be 3s1. So 3s1 would be the only valence electron that neon has available to it. Okay, now again, we've talked about the fact that chemical compounds will form simply because these electrons are lost, gained, or shared. I know I repeated that, but it's really, really important. The electrons that interact are in the highest energy levels, so incomplete, and the ultimate goal for electrons is to somehow end up with a complete outer shell. This is what makes them happy or lowers their energy. Now we're going to do a chart in class that kind of summarizes a lot of the valence shell patterns. So we'll do that together in class. All right, now for categories, some of these we've talked about, but for the metals, we split them up even further into the alkali metals, which are group 1, alkaline earth, which are group 2, the transition metals, which are mostly all of our D block elements, and then our rare earth elements, which fall in the F block, which are the lanthanides and the actinides. And our group 1s and our group 2s are all in the S block. For the non-metals, our halogens are group 17s, our noble gases are group 18s, and all the others, you'll notice both the rest of the P block is where the overlap for metals and non-metals takes place. So that's important there. And then our metalloids are also all in the P block, and they're also called kind of semi-metals. If you remember, back in Unit 1, we talked about some of the properties for metals, non-metals, and metalloids, and those still are important. Okay. The next thing that we've got in the S, just to summarize a little bit, in the S block, you have your alkali metals that are group 1 metal. We'll explain this with the valence electron chart, but they all end in S1, whatever energy level you're talking about. And here are the elements listed. They are very reactive since they only have one valence electron, and they just give that away. And they're typically not found as pure elements in nature. They're mostly found in compounds for that very reason. They want to give that electron away and make a compound. Now for the S block continued, the other S block metals that we have are alkaline earth metals that have a generic electron configuration of Ns2. For example, beryllium is going to be simply ends in the 2s2 for its electron configuration. They all follow that pattern. They're also very reactive because they have 2 valence electrons, and they're also not found as pure elements. They're only slightly less reactive than the alkali metals, but not very far behind. Then we have the last 2 elements in the S block, and that's helium and hydrogen, and they're really exceptions to the rules. Hydrogen we're not even going to get into very much now, just going to say unique because it only has 1 electron. It actually can give that electron away, and it's essentially 1 proton floating around in space. Helium does demonstrate the stability of the noble gases because it does still have that 1s2, that full energy shell complete, so it will demonstrate stability. It's just has much less mass than the other noble gases. Okay, for the P block, you've got groups 13 to 18. The only exception here is helium, which we put in the S block. The P block and the S block elements are called main block elements. We've already talked about, or we will talk about, their patterns and electron configurations, and the properties vary greatly, so we're not even going to really put any characteristic properties here because you start with metals like aluminum, you go all the way to the noble gases of nonmetals. So it's tough to put them into groups. Last 2 groups that we have in the P blocks that do have some patterns. First are the halogens. They're group 17. They are the most reactive nonmetals, and that's because they have 7 valence electrons. They only need 1 more. And if they get that 1 more, so for example, if you think about, they all end in P5, meaning that they've got 1, 2, 3, 4, 5, and they've got 1 spot for an extra electron. So if they can fill that extra electron, that's what's going to make them happy, if they can get that filled. And then they'll be like the noble gases, which is what everybody wants to do because they're the cool kids on the periodic table. And again, which gets us to group 18, the noble gases, which are unreactive because they're already happy. They've got that full set of electrons, they don't want any more. Okay, the D block we've talked about as well, and with the D block, they're groups 3 through 12. These are our transition metals, our typical metal properties such as being good conductors, they're malleable, they're ductile, all of those things. They're less reactive, and we may find them in nature as element. And if you look through the transition metals, you'll see elements that we're familiar with, things like gold, platinum, nickel, copper, all these things that come to mind when we think about metals. Okay, and then last but not least, we've got the F block elements, which we've also talked about being the rare earth metals, and that's just because we don't see them very often. The lanthanides are from element number 58 to 71, and then we've got the actinides, which are from 90 to 103. Really, the only ones we probably have heard of are uranium and plutonium. Other than that, The names are kind of cool, but nothing we really come in contact with on a very strong, on a regular basis.